and the first picture. What's the difference between the middle picture here and the first picture here? Carol.
He's throwing the ball at an angle, he's not just throwing it vertical.
He's not just throwing it vertical, he's giving it some horizontal. All right? Now, Carolyn, one last question. What do you know about the vertical part going up compared to the vertical part going down?
The acceleration is the
Okay, and the up path compared to the down path is the same. Last question, it's got a part two. What do you notice about the up path of this ball compared to the up path of that ball if this person was throwing it from here?
The ball on the first one, when you're throwing it up.
This one?
Yes.
Okay.
So is person that you're throwing the ball upwards?
This person has thrown straight up. Yeah.
Okay. When I'm throwing up, the ball is getting closer to them. Each second is closer to the other because the acceleration is slowing down the ball.
Okay. And how does that compare to over here? Yeah, right? Because this person is adding, excuse me, a horizontal, does that change the vertical? No. The vertical and horizontal are totally independent of each other. So if this person throws it straight up to some height, let's call it H. If this person throws it at an angle, but it reaches the same height of H, then the vertical portion of this matches this. Now, what's different about this path? Andy?
It's given a bigger horizontal velocity.
Yeah. Is there anything different about the vertical? No, because again, I'm here. The vertical for this is the same as the vertical for this is the same as the vertical for this. This has no horizontal. As Carolyn said, this has got a tiny horizontal. As Andy said, this is given a bigger horizontal part. So our horizontal motion is different for each of these things, but the vertical motion is the same. Yet they have no relationship to each other. The vertical does not influence the horizontal, and the horizontal does not influence the vertical. Now, obviously, time is probably the exception to that rule, right? So time is determined in the vertical. Yeah, obviously, it influences the horizontal motion. But we can have a certain vertical motion corresponding to different horizontal motions, right? So if we take that last thing, and we think of each of these things individually, all right, then in reality, what did we do yesterday? Yesterday, we took Emily's initial velocity here. What was it? Oh, it was 20, right? 20 meters per second. And that initial velocity was 20 meters per second at some angle here of 60 degrees. But we recognized that initial velocity that was at an angle had a horizontal component and it had a vertical component. We recognized that the horizontal component was the adjacent side of the trig triangle, so that the horizontal component would be your entire speed times the cosine of 60 degrees, and that the y component was the total speed times the sine of 60 degrees, or 20 times the cosine of 60 to give me 10, 20 times the cosine or the sine of 60. I think this was 17.3 meters per second, and this was, excuse me, 10 meters per second. Now, you did that homework sheet yesterday. The answers were posted up here, and hopefully one of the things that you recognized was, depending on where the vector was drawn and what angle was assigned to it, sometimes the x's don't always correspond with the cosine, and sometimes the y's don't always correspond with the sine, right? So in other words, maybe one of those things was, okay, we've got a vector that is, so if this is north and this is west, I think one of them said, there was a vector at 30 degrees west of north. So our vector would have looked like that. Well, look at my x component is there, and my y component is here. What side of the trig triangle is this y component? That's the adjacent side to that trig triangle. So now my y component here would be associated with cosine, while the x component would be associated with sine. So what you do not want to do is be wandering around generically memorizing this. You want to have an understanding of where we got to that and how we got to that. Okay? Now, the other way we can think about that is, okay, clearly there's some horizontal speed right here. Let's label that v sub 0 sub x. And clearly, since it's going up in the air, we've got a v sub 0 sub y. So if you're given, or you can look and visualize the knowledge that there are horizontal and vertical components, then to get the actual speed, you would put these two things together, and that would be the actual speed. Now, how have we done that in the past? We've taken this vector and we've moved it over here. The other way, you can just kind of like sketch out, it's called the parallelogram method, right? If you make a parallelogram out of those two vectors, your resultant is always at the diagonal to that parallelogram. Now, what do we know as this path is continued? What happens to this horizontal speed? It stays the same. So the horizontal speed here is also v0x. Likewise, that's why we ended up with 10 as the speed up here, right? Anywhere I go, my horizontal speed is going to be equal to what it was to begin with. However, gravity is slowing this down. So as the ball rises, that y component will change, right? Oops. It's no longer equal to v sub 0 sub y, it's some other vy. Up here, vy is equal to 0. And the down path mirrors the up path. So the y speed here would have the same size, just in the opposite direction. So it would be minus v0, or minus vy. And then over here, this is minus v initial. So conceptually, that's what we have going on. But as we've become accustomed to, we've got both conceptual and mathematical. So if we change our directives with respect to Emily here, we got basically 3 questions. And these are the basic 3 questions that are often asked with respect to angular projectiles. And as usual, right, there are variants of these that are more difficult, but the basics include, A, how long is the ball in the air? B, what's the maximum height of the ball? And C, what's the range? Now, range is a new term for us. It's important that you know what that term is. That's maximum horizontal distance. So range is maximum horizontal distance. Woo. All right, so let's figure out the answers to these things. Now remember, once we have our components here, we don't worry about the 20 meters per second anymore. Because anything we do in the x, we'd have a v initial in the x of 10 meters per second. And anything we do in the y, we'd have a v initial in the y of 17.3 meters per second. We can't mix and match the 10 and the 17, and we can't include the 20 in either of those, because the 20 is the combination of the 10 and the 17 acting at right angles to each other. We also know, obviously, then that our acceleration of the x is 0, and our acceleration of the y has to be negative 9.8 meters per second squared. Why? Can you tell me why the acceleration would be negative 9.8 meters per second squared?
If we assume that upward is positive, it would get positive, so the downward is in the opposite direction.
Great. And in this case, we have to assume upward is positive because we know the golf balls hit upwards. and we've assigned a positive number to it over here. Okay? How long is the ball in the air? Is that an issue horizontally or vertically? It's an issue vertically. Now, there's a few different ways that we can figure that out. Like one is way easier than the other, I think, right? So, how long is the ball in the air? Now, yesterday I hit that sign, didn't I? Not only did I hit that sign, the door was open, so there was only like half the sign to hit. This should be my child's play. Now, what's causing the ball? Well, the wall, I guess, actually, right? But if there was no gravity, what would happen to the ball when I hit it? It would just keep going. So gravity is what is causing this ball to have a finite time of flight. So it makes sense that gravity and its acceleration would have a hand in how long this thing is up in the air. So the easiest way, for us to think about this, the easiest way is to straight go here, right? Like, look at it. It's the vertical acceleration that causes this change in the y velocity to begin with. So then the time of flight would be the change in the y velocity, divided by a. Thanks. Now we know that the a value is negative 9.8 meters per second squared. That change in the y velocity, though, can be kind of tricky. Johnny, what's this mean right here?
What's that? Initial y velocity?
Its initial y velocity is 17.3 meters per second. Now let me get rid of this 20 to make it a little bit clearer here. Okay? So if I get rid of this 20, my initial y velocity right here is 17.3 meters per second. What's the y velocity then, John, at the end? Right here, the y velocity is 0 right before it hits the ground. The end is a relative term. Where's the y velocity 0? The y velocity is 0 at the top. Andy, what's the y velocity down here? 17.3 in the opposite direction, so it's negative 17.3. What's the delta? What's the change if the initial is 17.3 and the final is negative 17.3? Yeah, negative 34.6. Lots of people will say that that delta is 0, right? But that's incorrect. Like the number's the same, but the difference between having $17.30 in your pocket and not having any money in your pocket and owing somebody $17.30 is not 0. It's minus 34.6 meters per second. Right? Now, we get around, right? Our delta t is approximately 3.5 seconds. Because our delta v is about 35, and our a is about 10. 35 divided by 10 is going to give us 3.5. So our total time of flight is 3.5 seconds. What is happening for each of those 3.5 seconds horizontally? What's happening horizontally for each of those 3.5 seconds that the golf ball is in the air? Miriam.
Traveling at a velocity of 10 meters per second.
And if it travels at a horizontal speed of 10 meters per second for 3.5 seconds, how far does it go? 35 meters. Right? If we take a step back, that is relatively straightforward. Hey, that's the answer to question C right here. What's the range? Right? Well, look, we love our math. Delta x equals v initial t plus 1/2 ax t squared. The acceleration is 0. Delta x equals v initial x times t. So what's that v initial? That's 10 meters per second times a time frame of 3.5 seconds. Gives us a delta x of 35 meters. text. We use 34.6 and 9.8. We might get slightly different. I don't like the numbers anyway, right? In fact, like I like the numbers so little. Remember, this could be an answer. This could be an answer. Ooh, or we could get the even more complicated version of this answer. And quite frankly, it might be a formula that you'd see in a textbook. How long is that thing in the air? Well, this 34.6, this minus 34.6, is twice the initial y velocity. It's actually the negative of twice the initial y velocity. Well, what's the initial y velocity? V times the sine of the angle. So technically, this delta Vy is minus 2 V sub 0 sine theta divided by G. Do we want to run around memorizing an equation that says delta T equals this? No, because that's a very specific situation. When you have an angular projectile and it starts and ends at the same height. We don't want to run around with those specifics. Now, B is kind of cool. B is kind of cool because there are 3 or 4 different ways of doing B. What's the maximum height Emily's golf ball goes to? Let's take a stab at that. How am I going to figure that out? Emma, how am I going to figure that out?
So if it takes like 3.5 seconds for it to hold, more sense to take 1.75 seconds for it to reach the top.
Okay, concept number 1. The up path mirrors the down path, which means the time to get up to the top is half the total time. So Emmett says the time to get to the top is 1.75 seconds. All right, what's next?
It starts with the initial vertical velocity of 17.3 and at the top it's 0.
What's it?
The vertical velocity at the top of the graph is 0.
Okay.
So you do like the average of that period.
The average what?
Vertical velocity of that period.
Average y velocity is equal to delta y over delta t. What is the average y velocity over that period of time? It's the initial y velocity plus the final y velocity divided by 2. Yeah, let me do some different algebra first, right? How am I going to get delta y? It's the average y velocity times delta t. What's the average y velocity? It's the initial y velocity plus the final y velocity divided by 2 times delta t equals delta y. 17.3 plus 0 divided by 2, 8.65 times half of that time. Ooh, I'm going to say time to go up. All right, so 8.65 times 1.73. 1.75. And then that is what it is, right? So 8.65 meters per second times 1.75 seconds equals delta y. Don't care about it. But I do care about it because if somebody can find a different way. Anybody got a different way? I like that way. That's my favorite way. Carolyn, give it a roll.
Oh, I just have to have written down the bottom line.
8.65 meters per second. That's 17.3 plus 0 divided by 2.
What was the parentheses next?
1.75 seconds. Okay, look at it. If we look at these equations, we're trying to find delta y. We've already used this. Does it make any sense to use this? No, delta y is not there. Does it make any sense to use this? No delta y. Does it make sense to use this? No delta y. Is there a delta y here? Yeah. Could I use that? I could. Final y velocity is 0 at the top, 17.3, negative 9.8. Could I use this equation? Yeah, I know everything but that thing. So I could use Vy squared equals V initial y squared plus 2 times Ay times delta y. Or I could also use delta y equals V initial y times t plus 1/2 Ay t squared. 17.3, 1.75, negative 9.8, alert, 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 1.75 squared. And you go to any of those. Now your homework, you picked up on the way in. Everybody not pick up one of these things? Just don't bury it. Okay? And it's 4 questions. It isn't even due till Monday. Alright? I would highly recommend if you don't wait till Sunday night. The answers are posted up here. The first question on the cover, on the front, right, there's some notes. And then there's a horizontal projectile question. We've been through those. Let's take a look at the angular projectile question about Robbie Gould. Take a look at the angular projectile question about Robbie Gould. Now I'm going to help you set this thing up. I'm not going to get any answers. All right, those things are sitting up here. Emily, can you read that for me? Right, so first off, 25 meters per second at 50 degrees with the horizontal, so we got to recognize that's an angular path. Once we recognize that's an angular path, 25 meters per second and the 50 degrees are really just going to be a means to an end. We can never use the 25 meters per second in any particular problem that has to do with the x or the y, because the 25 meters per second is not in the x or the y. So our first step is part A, right? Draw the initial velocity vector and calculate its horizontal and vertical components. So part A, right, well here is 25 meters per second at an angle of 50 degrees. So we've got an x component. What side of the triangle is that x component? Adjacent. Adjacent, and we know the hypotenuse. So the trig function that relates adjacent and hypotenuse is cosine. So what's this x component? It's the full speed, v sub 0, times the cosine of the angle. Or in this case, 25 meters per second times the cosine of 50 degrees. Make sure your calculator is not in radian mode. And likewise, it also has a y component. V sub 0 y is v0 times the sine of theta, or 25 meters per second times the sine of 50 degrees. Okay? I'm thirsty. I'm going to go get a drink. All right? Get those 2 answers while I go fill up my water. Isabel, you got numbers for this? What did you get for the x component?
16.07.
We'll call it 16.1. And what did you get for the y component?
19.15.
We'll call it 19.2. You got confirmation on those two? Okay, good. Now from there, essentially, like, you can fill in this chart a little bit, right? You don't have to fill this chart in every single time, right? What's our initial x velocity? So our initial x velocity, right in that box, is going to be 16.1, and our y velocity, our initial y velocity, is going to be 19.2. Our acceleration in the x is 0, and our acceleration in the y is going to be negative 9.8 meters per second squared. Let me see if I can get one of these questions. It's gonna be- All right. A, B, C. So our A, B, and C over here are essentially B, C, and D for our example, but they're out of order a little bit. So look at B on your worksheet. Calculate the maximum height reached by the football. Is that A, B, or C on Emily's question? That's B. Now, what do we know about B? What was kind of special about B? There was at least 3 different ways to do B. Evan chose to use this average velocity equation. We could use this V squared equation. We could use this delta Y equation. With Robbie Gould's situation here, which of those does it make the most sense to use? Anna.
The B squared.
Why does it make the most sense, Robbie Gould, to use this? Anna. As of right now, we do not know the time. So in your head, if you chose this, you'd run into a roadblock. Could we figure out the roadblock? Yes. Does it make any sense to deliberately go to a road that has a roadblock? Not when you have another option. Yeah, but here's the thing, right? You could face a question that is only calculate the height of the football. Right? So do we proceed to go on and do the other stuff? Yeah. Okay, but we gotta face this as a problem solving situation. Do we want to refine our problem solving? Right? So like I had to go out to Clarence Hollow. I think maybe we were going to eat at the Clarence Hollow Bistro, maybe, right? Anybody live out near there? Right? So you know that Salt Road is closed, maybe, right? From Griner to Maine. So the first time we went out there, I'm like, okay, I'm gonna go up Griner, and it's and make a right. Guess what? It's closed. So then what did I do? I doubled back to Bank Street, then I left on Bank, and then I went back up to Main Street, right? Now we went back to the same restaurant like a month later. Would it make any sense for me to go to Salt Road? No, because I already knew that Bank Street was open and Salt was closed. If then the second time I went to Bank Street or to Salt Road, could I figure it out and go back to Bank Street? Yeah. But if I already had that knowledge, why would I bother? So that's kind of what we're going to do. Why would I choose this when I know I don't have time? And I could choose this and I got everything else. Right? So for part B, you're going to do this. All right? Isabel, what's part C say for Robbie Gould?
Calculate the hang time for the football.
Calculate the hang time for the football. Is that A, B, or C here for Emily's problem? That's A. Now we're up here. So you can use this to figure out part C on that first question. Now what Emmett said is, well, I know I got to use the hang time anyway, so let me do that, and I'll go back and I'll use one of these things to get part B. Is that doable? 100%. But if your only question is part B, why would we want to do that? And in fact, some of the algebraic answers, God bless you, wouldn't even have time in it. So you might not even be able to do that from a standpoint of an AP question. All right. Jamie, what's D say? What's that correspond to up here, Jim? That corresponds to C. So how are we going to do that? We're going to take the initial x velocity and multiply it by the time we figure out in part C. And that's, like, look at those two things. That's the basics of all of this stuff. And as always, there's always some add-ons. I don't want to say always, right? Always the options for add-ons. The option here is part E. Zach, can you read part E for us?
Does Robbie go
So does Robbie Gould make the field goal, kick from the 30-yard line? Where's that up here on Emily's question? It's not. So we have our basics, and then we have some stuff that we got to think about. Here's the path of Robbie Gould's field goal. What conditions have to be met for that field goal to go through the uprights? Obviously, it's got to be on line. Andy.
It's gotta be higher than 10 feet by the time it reaches the field goal.
Yeah. I'd like to firm that up though. A little careful with it's got to be 10 feet high by the time it gets to the field goal. I would change one word, Al. Yeah, it's not by the time it gets to the field goals. It's at the time it gets to the field goal post. It has to be 10 feet high, right? Because look, if the field goal posts are located right here, wouldn't it have been high enough like here? Yeah, that doesn't do it any good. So what conditions have to be met? When x equals 40, so when x equals 40 yards, y must equal 10 feet or higher. Oh man, now we've got some added problems. The units create added problems, right? Because we've got yards and we've got feet, and G is calibrated in meters per second squared. So probably the way you want to do this is put x in meters, put y in meters, and then you got to figure out a way to see if Robbie Gould met that condition. Is it 10 feet high? It's going to be about 3.2 meters maybe. Is it 3.2 meters high when it has traveled about 36 meters in the x? That's what you got to figure out. So there's 4 total questions. We just did most of one of them. So you've got 3 total questions plus a little bit. All right? Not due till Monday. All right? So now, you can take a break, go to the bathroom, do what you need, and then get to work. And I'll walk around. Friday, we're going to drop this thing. You will have time tomorrow, and then we'll do time on Friday. But hopefully it's all wrapped up by tomorrow. Yeah. What? Drop that thing open. Yeah.